everyone. I'm here from DigitalOcean. Before we begin, I want to tell you a little bit about myself. My name is Sneha Inguva. I'm a software engineer at DigitalOcean, currently on the network services team, so we do a lot of work with software-defined networking. And that's a photo of my cat for absolutely no reason, but GitHub, Octocat, cat. So if you're not familiar with DigitalOcean, we're a cloud hosting company. We have about 12 data centers located all around the world, and we have a multitude of products. So for the longest time, we had compute, essentially virtual machines, storage, object and block, and most recently, we have, I guess it might be in beta, Kubernetes as a service, and more coming soon. We also operate at a fairly large scale as a cloud provider. We have more than 300 microservices in production today, about 1.15 million virtual machines. And in terms of metrics that are being scraped about our microservices and virtual machines, we have about 1.8 million metric samples being scraped every second. So with that in mind, I want to take you on a mystical journey through a time of change at DigitalOcean. So the past. This was probably even before I joined the company. Services were primarily run on virtual machines. We would often provision these virtual machines with Chef. We would deploy to them using Chef, bash scripts, some other weird combination. In terms of monitoring, we primarily had black box monitoring. So we used Isinga and Nagios. So this wasn't great for a couple of reasons. First of all, we would often spend more time writing Chef or editing Chef than writing actual applications. And secondly, we didn't actually have a lot of introspection into our services. Luckily, there was a change, and we entered a time of beauty and happiness. So now services have moved to largely, or I guess for a good chunk, largely running on in containers on Kubernetes. We also built an abstraction layer on top of Kubernetes known as DOCC, and most services are deployed to DOCC using the DOCC CLI tool. And on top of that, we've set up metrics, tracing, and centralized logging. So now we get a lot more observability into our production microservices. We can now actually tell if a service is up or down. We can trace a request through a multitude of services, especially if there's an error in our request. And we can also set up alerts based on metrics. This led us to ask another question, though. It's great that we have observability into production services, but what about services that we're just writing? New services. And so that brings me to the topic of my talk today, observability pre-release, using Prometheus to test and fix new software. So the plan today is we're first going to talk about observability at DigitalOcean. I'm going to dive into one of the pillars of observability, metrics, and talk about what we like to measure for metrics. I'll then go into Prometheus and talk about what exactly it is and why we like it. Finally, I'll get to the core of my talk, which is about the build, instrument, test, iterate loop, and I'll end with some examples to really illustrate kind of what I'm talking about. So starting with observability, I don't know when the term pillars of observability came about. I think it was like 3-ish, maybe 2-3 years ago in a blog post. But observability generally refers to introspection into a system or service, and the pillars of observability refer to metrics, logging, and tracing. So metrics, essentially a time series of sample data. Here we have a time series of peak go routines amongst certain instances of a microservice over time. Metrics are great in that we can apply mathematical functions to analyze data a little further. We can aggregate trends. We can also split up data by dimension. And we can configure alerts, especially threshold alerts. The next pillar of observability is tracing. So tracing refers to having timed operations known as spans and propagating that metadata to a variety of threads, requests, and processes. So here we have an example trace of a request that's going through the serve DHCP v4 operation, and we can kind of see how the request traverses and the latency of each component of this operation. This is useful in that we can look into causality, especially if we have latency issues. We can maybe look into the causality of that latency issue, like which microservice is contributing to that latency. We can also watch a single request traverse multiple services, and this was especially cool and something that happened, I believe, last year at our hackathon. We can actually use distributed tracing to build a map of our overall production ecosystem and kind of see how different services interact with each other. And the last pillar of observability is logging, which refers to a record of events over time. So above, you can see the logs over time, kind of a bar chart of north D. The unfortunate thing with logging is logs are often more difficult to store long term, but they can help you identify needle in the haystack type issues. So that's observability, but the focus of this talk is metrics. So I'm going to talk about what metrics we like to measure. So if you've read the Google SRE book, Site Reliability Engineering at Google, awesome collection of essays, you've probably heard of the 4 golden signals, which refer to key metrics for a request-based system. So they refer to latency, the time to service a request, traffic, the number of requests per second, often broken out by the type of request, error, just error rate of request, and saturation, often a little bit more difficult to understand, but it refers to fullness of a service. There's, of course, the use metrics for resources. I believe this acronym was coined by Brendan Gregg. And use refers to utilization, time a resource is spent servicing work, saturation, maybe the extra work that a resource can't service, as well as error rate, just similar to before, just the rate of error events. And Brendan Gregg, this is a quote that people state time and again, use metrics allow users to solve 80% of server issues with 5% of the effort. So it's something we definitely care about and have leveraged heavily at DigitalOcean. So those are our metrics that we care about, but how do we measure them? And that's where Prometheus comes in. Here's the beautiful Prometheus logo. It is a pull-based metric solution. Pull-based meaning the Prometheus instance actually scrapes metrics from our targets of choice rather than the targets of choice or the services pushing metrics to our monitoring solution. So the push versus pull debate is something that has been around forever, but I'm not going to go into that right now. Prometheus is also written in Go, and it has an alerting solution, Alert Manager, which is often deployed alongside Prometheus. We absolutely love Prometheus at DigitalOcean. We currently have actually more than 85 instances of Prometheus in production. We have a data center-wide monitoring system known as Pandora, and we also use Prometheus to monitor different services in our stack. And as I mentioned before, we're scraping about 1.8 million samples per second, so a lot of data. The reasons we love Prometheus are, A, it's easy to deploy. As I mentioned before, it is written in Go, so you could deploy it as a Go binary to a virtual machine, or you can containerize it and deploy it on something like Kubernetes. It's flexible and extensible. It has something called labeling, which is extremely helpful in the Kubernetes ecosystem when you have things that are deployed in pods. It also has a lot of service discovery mechanisms, also helpful, especially given that we have Kubernetes at DigitalOcean. We also have Mesos, and then we often have things that are being scraped statically. And I guess one of the most important things is it has a very strong query language known as PromQL with a variety of functions. At the base of Prometheus, there are 4 core metrics: counters, which is essentially monotonically increasing value; gauges, a numeric value that goes up or down; histograms and summaries, which are fairly similar and refer to a bucketized count of observations. Using these 4 core metrics, as well as the PromQL functions, you can actually achieve all of the 4 golden signals as well as use metrics. So we can use counters, apply the rate function to them, and get error or request rate. We can often break this down by type of request as well. We can use gauges to get utilization metrics such as CPU or disk usage or memory usage. And then lastly, we can also get latency metrics using histograms or summaries. And we often like to get 50th percentile latencies, but also 95th and 99th to kind of see what the long tail of our users are experiencing. So that is what Prometheus is, but now we're going to finally get to the core of my talk, which is our build, instrument, and test and iterate loop, or how we build services. So first thing we typically do, design a service, submit an RFC, get some feedback for the RFC. We then write our service in Go, which is the language of choice at DigitalOcean. We do use other languages, but a lot of our work is in Go, and we have a Go mono repo as well, I believe, that's been written about. We have a lot of internally shared libraries that we leverage as well, and here's kind of an example of one of them, DRPC, which is our shared RPC library. We love our shared libraries simply because we get a lot of things automatically. With DRPC, all our RPC services already have a logging, metrics, and tracing interceptor incorporated, so we can actually get relevant, I guess, metrics about our RPC services, such as latency, request rate, whatnot. We also have traces or spans that are sent to our trace collector, and we have logs that automatically get sent to our centralized logging system. Very helpful. But on top of these shared libraries, we often also have to instrument our services. So we might have to explicitly configure our services such that logs get sent to centralized logging by logging to syslog. We have spans, or our timed trace operations, that are sent to our trace collectors, assembled, and then sent to our tracing backend. And then we also have to configure our Prometheus metrics. There's two ways we go about that. There's, of course, the Go client for Prometheus that we definitely leverage, and then simply just register these metrics with a global Prometheus registry. So above, we have an example of the gauge metric. It's just a value that goes up or down, and it kind of talks about the number of converged chassis, which we don't have to really worry about what that metric means. Just know it's a gauge metric, and that value can go up or down, and it's not necessarily aggregated. The next way we set up metrics is by using the collector interface. So the collector interface is this structure that essentially is, you can implement this collector interface, and the structure that you use to implement it typically has two functions, and the collect metric is key. It basically shows us that every time Prometheus scrapes your instance, the collect function is called, and metrics are sent to that particular channel. So using the collector interface, we often do one of two things. We often just build out a third-party exporter, or we use a third-party exporter. So we use MySQL, RabbitMQ, and the node exporter just to get virtual machine metrics in a lot of our components. So those are three exporters we definitely use. And the OVS exporter is one of the examples of things that we've built out to get some SDN metrics. We also use the collector interface internally within our code, and here's an example of a rate limiter we built out, and I'll get to this example a little bit later. The key things to note about this is we actually have some data that we're collecting internally within this structure, but then we're exporting, and we're kind of providing a snapshot of request rate metrics every time Prometheus scrapes this service. So once we've implemented our service, we build a ton of dashboards. Seriously, this is a lot of dashboards. So the first dashboard I'm going to show you actually is our master dashboard of sorts, and it links to all the components that are in the system. This is for VPC. So we've got our state metrics, just what is up or down in our system, like the number of components that are up or down. And then we've got links to console, our load balancer dashboard, our MySQL dashboard, and one of our Go microservice dashboards, NorthD. For our services themselves, you can see that we're definitely measuring the 4 golden signals. On the left-hand side, we've got request rate, and it's split out by type of request rate. As you can see, we've got sync initial chassis, I believe converge all chassis. And on the right-hand side, we've got request latency. And once again, also important to note, we've got 50th percentile, but we've also got 99th percentile to see what the long tail of users experience. We also have our use metrics. We've got number of Go routines, CPU usage, memory, disk usage, a lot of these utilization metrics. And as I mentioned, we also use MySQL. So we also have use metrics as well as request rate metrics for our MySQL database. So we've got queries per second and the number of MySQL connections that we have. And just when you thought there couldn't be no dashboards, there were still yet more dashboards. So we also have saturation metric for our queues that we're using. And saturation, I mentioned, is something that's often a little trickier for people to understand, but hopefully this example gives you an idea. So we've got RabbitMQ queue depth as well as the message status. So what is kind of our ratio of unacknowledged messages versus ready messages? So once we have our dashboard set up, we're ready to start testing. And so we do 3 types of testing. Load testing. It's definitely possible for us to build some sort of load tester, but we find that given that a lot of our services are RPC services, we can simply have a number of concurrent gRPC clients and then have them send requests to our RPC services and Go routines to have a sufficient load generated. We also do a lot of chaos testing, given that every component often is part of a larger system. So we like to see how failover occurs or how recovery occurs when a component goes down. And of course, we also do a lot of integration testing, especially on the networking services team. We kind of work at the bottom of the stack, largely operating on the software-defined network, on the hypervisor. So it's very important to ensure that any new service that we push out to production integrates well with the rest of the cloud. So testing is very helpful in that first, we can identify key issues. So here are some questions that we often get while testing, and you'll actually see this in some of the examples that I go through later. How is our latency? Maybe if we have a latency spike, we can use tracing to dig down further. Is there a go routine leak? This is also something that has happened, and we ended up using a worker pool. We can also see if there's a resource spike with traffic and use a different tool, CPU or memory profiling, to drill into that. We can also tune metrics with testing. So quite often, we'll go through a process of load testing or chaos testing and realize that a lot of metrics that we configured were actually useless. So we could just stop collecting them. Conversely, we occasionally realize that we don't have enough of a particular type of metric, so we instrument our service a little bit more. And then something that I mentioned that we love about Prometheus is the fact that there are labels, which allow us to actually slice and dice our data in different dimensions or aggregate them across different dimensions. So quite often, we also test and realize we need more labels to get better introspection into our services. So we end up adding labels to our data. We also end up tuning alerts. And this is especially useful, I believe, with load testing, occasionally chaos testing, because we can see exactly at which point our service fails and set up threshold alerts based on that. We can also do state-based alerting, just generally very important for on-call engineers. And the final thing, no one really particularly likes writing documentation, but it's very important. And so I think especially for the last two products I've worked on the networking team, at the tail end of doing a lot of recovery testing and load testing, we ended up writing a lot of operational playbooks so that when we went on on-call rotations, we wouldn't have any trouble. So here's kind of an example of some of the documentation we wrote about recovery testing for one of our Go services, NorthD. So once we go through all of these steps, building our Go services, instrumenting them, writing dashboards, and testing them, we like to iterate. And I think the best way to showcase how we iterate is just by going through some examples. So that kind of brings me to the last part of my talk. So the first example I'm going to talk about is DHCP. This is something all of your routers do to assign IP addresses to network interfaces. We also ended up, or in the process actually, of working on a DHCP server to assign IP addresses to the interfaces of our virtual machines or droplets. So our DHCP server is called HVadderD, and it's a daemon that exists on every hypervisor. So it has three components. It has a gRPC service that receives RPC requests from something called HVFloaty higher up in the stack, also a daemon that exists on the hypervisor. And then we have a DHCP v4 and DHCP v6 server that receives just general DHCP traffic over the OVS bridge, which is our virtual bridge on our virtual switch, from customer droplets. So the main, I know this can be a little complicated, maybe if you're not familiar with SDN, but the main takeaway from this is that HVadderD receives customer DHCP traffic, so we should probably load test it. So we did that. We sent a ton of DHCP discover messages to our DHCP server, and lo and behold, it fell over. There was a spike in memory usage and CPU usage, and then we managed to it. We realized a couple of things at this point. One, we needed more data. So we actually had to drop down to the Ethernet frame level for the DHCP server so we could do a lot of validation testing on, or some validation testing on our requests that we were receiving. So we ended up exposing some of those metrics, namely the number of bytes that were being read and written at the Ethernet frame level. And so once we implemented that, we were able to see those results when we load tested again. We can kind of now see we've got bytes read and written. Actually, none are being written. The next thing we did is we realized that we were having a service that ended up ooming when we were having a lot of load sent to it. And part of the reason for that is because we were spinning off a new Go routine to service every request. And in that Go routine, we were allocating memory. So we ended up using a worker pool to limit this. So we had a buffered channel, and we were basically just reading off requests from our buffered channel to process requests. This ended up helping a lot in terms of resource usage and our service falling over. We still, however, realized that we absolutely needed to detect bad actors and kind of account for the case where a bad actor could just very quickly send a ton of requests to our service and take it down. And that's where this rate map collector came in. So we implemented a rate map structure. It essentially calculated an exponentially weighted moving average of request rate, but on a per client basis. And then on top of that, it had a rate map collector internally, which would expose a snapshot in time of the request rate distribution across clients. So this is important to note, and we wanted to do this way because there could potentially be a cardinality problem if we attempted to use traditional Prometheus histogram metrics for this. The result of this is that when our rate limiter would rate limit a particular client, we would emit a log line. That log line would go to centralized logging, and we would use a last alert to alert users that an abusive actor was discovered and they were rate limited. So the final result is when we load tested again, the service didn't fall over, and that client got rate limited immediately. Yay! So hopefully the conclusion you can reach from this is that we load tested our service, we used metrics to identify some resource spikes, and then as a result of using those metrics, we realized we needed more metrics. We ended up building a rate limiter, we ended up using a worker pool to limit resource usage, and we set up alerts. So metrics were very key in helping us identify issues and ameliorate those issues. The next product I want to talk about, also a networking product, it was released earlier this year, is called VPC, or Virtual Private Cloud. So that's a fairly complicated architecture. Maybe the main takeaway from this is there's a lot of components. There's a MySQL cluster, there's the RabbitMQ queues, bunch of them, and there are workers reading from those queues, and also a bunch of services sending things to those queues. First thing we did was also load test this with a tester that has lovingly been named the Hammer. We are sending a ton of requests to Northd, as you can see, also resulting in a ton of requests, and RabbitMQ resulting in a lot of stuff being read by Southd. First thing we noticed is that as load testing started to increase and the load to Northd increased, there were some latency issues with different RPC calls. We decided to dive into that further using distributed tracing, one of our favorite tools. We ended up looking at the sync initial chassis call in particular, but noticed that we were actually load testing so quickly, in fact, that some of our spans, our timed operations, were being dropped, so we couldn't actually assemble a full trace. So we actually had to slow the load tester down a little bit. We did, and we were able to assemble a full trace, and as this quote from my colleague illustrates, we had an issue with MySQL, or just terrible queries to MySQL, rather. So we kind of fixed the queries that we were doing and able to improve our latency. One of the other things that we often don't think about is the fact that we actually may not need a queue. So even when load testing, our queue depth pretty much stayed pretty low. And I think that common sense usually dictates if your queue depth is pretty high, or your queue tends to run full, especially during load testing, you might need to push more work to the edge. But if your queue consistently remains empty, it's actually just working as a slow load balancer, so you might really not need it at all. There's also, as I mentioned, a ton of components in VPC, so we did a lot of chaos testing. So our Northd services were running in sort of a failover mode, so we induced a Northd failure, saw what happened. We dropped databases, tried to recover, saw what happened there, and then we also just killed off a bunch of Southd service workers and tried to see what would happen to our queue depth, and also if other workers would be able to pick up the slack. The result of this is we realized we needed to add a lot of alerts. We added our state-based alerts, just Southd down, Northd down, things like that, or perhaps down to a certain number of instances. We also added threshold alerts. So this was especially key when the MySQL databases were being dropped. We added some alerts to indicate that the replication was delayed. So hopefully you can see for VPC, we went a little further. We did both load and chaos testing, and we clearly also combined, so we used metrics to first identify that there was a problem, and then we used tracing to dig down further and identify where the problem was and fix it. And then lastly, we were able to configure useful alerts. So I know this is a lot of content. There were a lot of graphs. There was some Go code. Maybe that was unnecessary. But hopefully what you've gained from this is that the things we care about and the things that we like to measure are the 4 golden signals for our request-based systems and use metrics. We also like to instrument our services as early as possible. We could have, I think we should do this earlier even still at DigitalOcean. Quite often people wait a little too long, but I firmly do believe that instrumenting as early as possible with metrics, tracing, and logging, and then testing can help you identify problems, and especially performance problems, far earlier than before you release. And of course, combining your metrics results with profiling, logging, and tracing helps you dig a lot deeper and go a little further into identifying what might be wrong. So that's pretty much all I have. Thank you. Another cat.